Okay, so good afternoon or good morning or good night. Good night, Professor Kim. I know it's almost midnight in Korea. That's the trouble with the online conferences. We don't know how to greet the participants. It depends on where they are located. So I must say that I'm very happy to introduce Prof. Kim today, and also very disappointed because unlike the previous events that we attended together, I cannot meet in person with Prof. Kim and with all the other participants to uh, iiWAS to iiWAS event. But I'm very excited because who is a better professional to tell us about the AI and big data convergence than Prof. Kim? I have known of Prof. Kim before I could meet him. When I was a student, I read his work on object-oriented databases. And already from the 1980s, he was looking at not only the convergence of technologies, but also at both the research and the industrial side of what we are doing. He worked at IBM Almaden Research Center. He worked at MCC, where he worked on the Orion project. And he also is the founder of UniSQL. Of course, many of you know Prof. Kim because of his active participation in the database research world. He was the ACM SIGMOD chair. He's a founding chair of ACM SIGKDD. He has also been editor-in-chief of ACM Transactions on database systems, and is a founding editor-in-chief of ACM Transactions on internet technologies. So again, probably one of the best researcher and computing professional to tell us today about the convergence between two major trends that we hear a lot about independently, AI and big data. But then, Prof. Kim, please answer for us the question of what shall we expect from ABC? Let's welcome Prof. Kim. Prof. Kim, you have the floor.
Yes. Thank you very much, Professor Bressan, for your kind introduction. It's a great pleasure to give a keynote in iiWAS MoMM 2021. I would like to thank Professor Ismail Khalil and Professor Gabriela Coates for inviting me to talk and agreeing to have me and Professor Woong-Kee organize the ABC Forum. In this keynote, I will present my personal views on the AI and big data convergence. To make it easy to remember, I will abbreviate AI big data convergence to ABC, since everyone knows ABC. I will outline my ABC vision. Then I will discuss some inspirations that have led to this vision and some technological challenges and research opportunities this vision entails. First, I will motivate and define the ABC vision. During the past 70 years or so, the focus of computing has clearly shifted from numerical computing to data processing. Over the past 20 years or so, data processing in turn has advanced to smart data processing. In my view, if we realize the ABC vision, the smart data processing will take a significant step forward more quickly. The ABC vision consists of two key components. One is AI and big data leveraging each other. Another is the fuller uses of data, which I will explain shortly. In the past 40, 50 years, AI and big data each has formed a separate R&D community and separately evolved and produced important technologies. The scope of big data has included data modeling, data integrity protection, dealing with large volumes of data, variety of data types, data integration, data security and privacy, and high performance techniques and architectures. In the meantime, the scope of AI has included machine learning, deep learning, natural language processing, computer vision, data semantics analysis, knowledge representation, and so on. I believe AI and big data can benefit from each other and can and should help each other. By the fuller uses of data, I mean the use of higher quality data and multimodal data. Each of these will significantly help both big data and AI. Higher quality data means data prepared for use, better prepared for use by both AI and big data. It includes cleaner data, richer metadata, and better organized data. The use of multimodal data will add an entire new dimension to both AI and big data. In my view, AI, big data, and mathematics have always pursued a shared goal, namely understanding the meaning of data. In that sense, the ABC vision is a logical continuation of this shared goal. The central goals of AI have been to understand the meaning of text and images, as well as to mimic humans' ability to learn and to represent human knowledge to support other goals. The goals of big data have been to capture the meaning of data in data models, to protect the integrity of data, as well as to support fast, targeted queries and updates. One goal of math has been to quantify the meaning of numerical data and the relationships between collections of numerical data. The realization of the ABC vision will significantly broaden the scope of applications of smart data processing, increase application development productivity, that is, make it easier and faster to develop such applications, improve application performance both in terms of speed and accuracy, and enhance the quality, usability, and security of data. Now, I will briefly highlight some of the inspirations that have led to my ABC vision. The big data community now has to contend with added challenges beyond the traditional challenges. One challenge is due to the proliferation of new data sources, including smartphones, body wearable devices, a wide variety of sensors, CCTVs, etc. This has led to additional data types to model and manage, including free text, audios, images, photos, videos, maps, and various semi-structured data. The rapidly increasing data volumes and data velocity have compounded these challenges. I would like to define multimodal data simply as a mix of two or more different data types. Often, the different types of data must be synchronized in time and/or location. There are already many widely used multimodal data applications. I think there's a huge number of potential multimodal data applications. One application that everyone knows about is the automobile navigation. It manages a mix of map data, time data, voice data, and graphic data that are location synchronized. Another application is the much hyped driverless vehicle. The driverless vehicle uses a variety of sensors, including the LiDAR, radar, sonar, GPS reader, camera, etc., to acquire data about all the important objects around the vehicle, as well as the location and speed and orientation of the vehicle in question. The multimodal data acquired by the sensors, along with the map data, are used to create a 3D map around the location of the vehicle. I believe the deep learning revolution we witness today would not have been possible without the open source machine learning and deep learning software libraries and the amazing advances in computer hardware. The open source libraries include NumPy, Pandas, Matplotlib, Seaborn, Scikit-learn, TensorFlow, Keras, PyTorch, RStudio, etc., etc. These powerful software libraries hide the not so palatable mathematics and democratize machine learning and deep learning. Unfortunately, machine learning and deep learning are far from being magic. It's very difficult to obtain actionable insight from data. You have to set the objective first, and you have to make sure you have data that can meet the objective. And beyond that, there's a bewildering number of choices to experiment with. Data scientists and application developers need lots of help. There may be lots of data samples, and there may be lots of features in each sample. The data set may be skewed, may contain lots of dirty data, and there are lots of elements in the all-important data pre-processing. There are lots of learning models. There are lots of model parameters. There are, and different learning models come with hyperparameters. There are lots of model evaluation metrics. There are lots of cost functions and activation functions. There are lots of nodes and layers in neural network architectures. All these require lots of experiments. Next, I will discuss some technological challenges, which is another way of saying R&D opportunities that can lead to worthy results. The initial scope of the ABC R&D I have identified includes the following: multimodal data management, semi-automated machine learning and deep learning, high-performance machine learning and deep learning, enhancing the quality, usability, and security of data, new smart data applications and services, and to reflect all these, extending the open source software libraries and improving the software and hardware architectures. In the remainder of this talk, I will discuss some of these. First, I'll talk about enhancing the data quality. The big data community has made substantial efforts to understand data and ensure integrity and security of data. These include data normalization, integrity constraints, triggers, authorization, transaction management, etc. The big data community can take this to the next level by leveraging the results and experiences that machine learning and deep learning have to offer. The machine learning and deep learning have techniques that can quantitatively identify correlations between attributes, identify outliers and dirty data, and clusters of data. The quality of big data and metadata can be much improved using such results. Python matplotlib library offers the boxplot function to visualize the distribution of data and identify outliers. The black dots in this picture are the outliers, data that lie outside of the maximum and minimum values of normal data. The techniques that establish correlation between attributes include the Pearson correlation, Spearman correlation, feature importance scoring, Seaborn correlation heat map, the select K best class in classification and regression, the cosine similarity between text vectors or documents, cluster analysis, etc. This is an example Seaborn correlation heat map. It's a powerful tool to visualize the quantitative correlation between each pair of features in the training data set. Since there are 19 features in this example, it must be difficult for you to see the numbers in the heat map. So I will magnify a small portion of this heat map. As you can see, each cell in of the heat map contains a number. The number is the correlation magnitude between the column and row features. For example, there's a price range feature or attribute, and its correlation with let's see which one, PC, or number of cores, let's say number of cores. The correlation magnitude is 0.0044. So there's not much of a correlation. The cosine similarity is used to measure how similar the text vectors are, regardless of their sizes. Mathematically, it measures the cosine of the angle between two vectors projected in a multidimensional space. Next, I will discuss multimodal data management. Multimodal data is required to present a holistic view of data in many situations. It is also often necessary to augment or confirm decision-making with or without machine learning and deep learning. For example, the result of a machine learning model, such as for predicting accidents in various parts of a city, should really be checked against other data, such as some statistical data, images and videos of the accidents and surrounding locations, etc. Also, machine learning and deep learning results can be enhanced by combining or correlating different learning models for different data types. It would be great if we can create common data models and APIs for some of the widely used data types, such as maps, photos, even genomes, etc. Availability of such APIs in the form of open source libraries should significantly facilitate development of multimodal data applications. Multimodal machine learning is in its infancy, but it can potentially lead to worthy results. The results of different learning models for different data types may be integrated into a single model, or they may simply complement each other without being integrated. Next, I will discuss semi-automated machine learning and deep learning. As mentioned earlier, in machine learning and deep learning, there are so many choices to experiment with. A full automation of the machine learning and deep learning process is simply not possible. However, parts of the machine learning and deep learning process can and should be automated. The pre-processing of the training data set is 80% of machine learning and deep learning process. If this is not done right, the results will be worthless. Let's take a quick look at the key elements of data pre-processing. They include data restructuring, data value changes, feature engineering, and data reduction. Data value changes in turn includes cleaning dirty data, disposition of outliers, text pre-processing, data discretization, data normalization or scaling, categorical data encoding, and so on. And feature engineering includes feature creation, that's creating additional features beyond what's given in the training data set. And feature selection, that's selecting useful features out of the whole bunch of features in the training data set. And feature reduction. And data reduction includes feature removal, data filtering, data summarization, concept hierarchy, data compression, and numerosity reduction. Numerosity reduction in turn includes data sampling and storing only the regression parameters rather than the entire data set, etc. Such steps as data normalization or scaling and categorical data encoding, each in turn has several algorithms to choose from. They may all lead to different results. Data normalization techniques include standard scaling, robust scaling, min-max scaling, absolute max scaling, decimal scaling, log normalization, vector normalization, etc. And categorical data encoding includes one-hot encoding, ordinal or label encoding, dummy encoding, hash encoding, etc. Different combinations of these techniques should be tried, and this should really be automated. Further, different combinations of the features in the training data set should really be tried, especially for clustering. This too should be automated. There's a strong need to semi-automatically run many combinations of the machine learning processing elements, pre-processing elements, models, parameters, etc. The current challenge is to substantially reduce the manual trials and tribulations on the part of the data scientists. The current open source libraries should be extended with libraries that semi-automate the machine learning and deep learning process. Finally, I will discuss high-performance machine learning and deep learning. There are three software approaches to high-performance machine learning and deep learning. First is data reduction using various techniques I already mentioned. Often, the use of much smaller data set can deliver the same result much faster than using the original much larger data set. Data reduction techniques can substantially reduce the computation costs. Second is more efficient learning models and algorithms. Third is distributed and parallel processing. There's actually another approach to high-performance machine learning and deep learning. It's the special hardware support, for example, for linear algebra libraries. But here, I will only discuss parallel processing. I must note that already there are well-known hardware support and customized libraries for machine learning and deep learning. NVIDIA offers the GPU, the CUDA framework, and the CUDA Deep Neural Network library for deep learning. There are high-performance linear algebra libraries such as BLAS or basic linear algebra subprograms and eigen. Also, scikit-learn library includes various classes with the n-jobs parameter to allow for multiple jobs to run in parallel. Unfortunately, just like machine learning and deep learning are not magic, parallel processing of machine learning and deep learning is not magic either. It takes a lot of work to realize the benefits of parallel processing. All worthy opportunities for parallel processing should be identified, and machine learning and deep learning algorithms should be modified for parallel processing. The big data community should be able to make some worthy contributions to parallel processing, machine learning, and deep learning. There are many opportunities for parallel processing. For each learning model, there are often many model parameters. For example, for a decision tree, the model parameters used in tree induction include the impurity criterion, specifically the Gini index and entropy, maximum depth of the tree, minimum samples for splitting the node, maximum features to consider, maximum number of leaf nodes to allow, etc., etc. Many combinations of these parameters should be run concurrently. Many learning models come with hyperparameters. One is the K, as in the K nearest neighbor classification algorithm, K means and K medoids clustering algorithms. Support vector machine uses different kernel functions, and each kernel function comes with parameters. And support vector machine also has the soft margin hyperparameter called C. Then there's the learning rate in gradient descent and backpropagation. There's the tuning parameter, lambda or alpha, in regularization. The data scientists have to try many values of the hyperparameters. The scikit-learn grid search class makes this easier. However, different values of the hyperparameters should be run concurrently. Machine learning and deep learning models involve computations on each and every individual data sample in the training data set. These include linear algebra operations, such as matrix multiplication, Euclidean distance or Manhattan distance between data points for classification and clustering, computations of mean, variance, and standard deviation, Gini index and entropy, computing the loss and gradient, etc., etc. The data set may be split, and the same computations may run concurrently on each split data. For validation and test, the training data set is split into train set and test set. The default is 75% train set and 25% test set. However, various split ratios should be tried. For k-fold cross-validation, the k is the hyperparameter to experiment with. Also, there's more than one quality metric for a learning model. For example, the silhouette score, purity, etc. for clustering, R squared, root mean squared error, mean absolute error, etc. for regression. Various validation and test parameters and options may run concurrently. In closing, I'd like to emphasize that most of the topics in the initial scope of R&D I've identified are already active R&D topics. I think this is great because the current work will form a strong launching pad for future R&D. I believe a greater focus and wider participation by the big data and AI communities will accelerate progress toward the next step in smart data processing. Thank you for attending my talk. I hope all of you will remain safe and we will soon return to the normal life that we knew until about 2 years ago. Thank you.
Thank you very much, Prof. Kim. So maybe before I open the floor, I would like to come back to one of the points that you made about AI. You talk about the advances in the hardware and in the high performance computing aspects. So I'm wondering, what are your thoughts about where to look at the next progress? In other words, should we first focus on leveraging the power of the current hardware, which allows us with sensors to collect the big data, with all the storage mechanisms to store the big data, and with the parallel computing to compute the AI models? So should we try and leverage the existing state of the software, or do you foresee a dramatic evolution of the hardware again that we need to focus on? I'm thinking, for instance, about systolic arrays, and maybe new models are going to come. So what should we watch? The current software and more, the current hardware and more software, or look at new hardware?
That's a great question. I believe that we have not really taken full advantage of the current parallel processing framework, hardware and the software framework. So the first thing that we should do is to try to maximize, to try to get as much out of it as possible, and then in that process, I believe that certain other possibilities will open up that can lead to a better and improved hardware.
Thank you very much.
Yeah, for example, the systolic array was long ago proposed for database processing, but it went nowhere. I think that the CUDA framework is fine, but we have to make good use of it. And there's a lot of hard work ahead.
Thank you. So that's good news for those of us who are working on the software part then. Are there any questions from the audience? You can either indicate your question in the chat or open your mic. Andrea, I believe the participants can open the mic.
Yes, they can.
Yeah, and maybe also try to open your camera.
I think the audience is all in Korea and they're asleep.
So Sandra, you want to ask a question? Please go ahead.
Also on my camera, thank you very much. I have a question to Professor Kim. 안녕하세요. And my question is, for example, you mentioned autonomous driving. Do you think we will stay in the automated level, or will we ever go to the autonomous level, to the final level of, for example, autonomous driving? Thank you very much.
I think that, again, we have to take an incremental approach. That is, full automation is just not possible because people with knowledge about data and the meaning of data have to look at the data very carefully and try to match that up with the objective of doing the machine learning. And it takes a lot of domain expertise, and I don't see how that can be automated. But there are so many algorithms, and none of them is the best for all situations. So it's just like data structures. So there are lots of data structures, but there's no one best data structure for all situations. So it's the same thing here. So I think that we can identify some small things, such as, for example, in my machine learning course in my university, I asked students to try to automate the various combinations of scaling techniques and categorical data encoding techniques. So, there are, let's say, about 6 scaling techniques and 2 or 3 encoding techniques. And you combine them all, you got 6 times 3, so 18 combinations. And it's very tedious to try to do all these combinations by yourself. So you should create a software framework and have all those done at the same time. So we can identify some opportunities like that. And then that, I think, once we can assemble them all, we can make some bigger progress.
Thank you.
Thank you
I think Rolando has a question. Rolando, you want to take the mic and maybe open your camera? Rolando Melo. No, Rolando, are you with us? Okay, so maybe Brahim Hubi wants to take the floor now for his question. Brahim, welcome.
Thank you very much for this interesting and exciting talk. My question is about data reliability. How AI and big data could deal with this concern?
I didn't catch the first keyword.
My question is about reliability, data reliability.
Reliability?
Yeah.
Data reliability. I don't know. I think that you can determine the importance of features with respect to the target. So you can have the importance score, but that's not about reliability. It's a relative importance of features or attributes in a training data set. And now, if you look at that, then you might be able to identify certain features or attributes that are very similar and therefore may be redundant. And so you can use machine learning techniques to eliminate certain redundancy in your data. But as for the reliability of data, I think it's a very difficult thing. I don't think the current AI technology has any solution for that.
Okay, thank you. Thank you.
Very soon, I'm going to leave the floor to Prof. Woong-Kee for moderating the ABC forum. But maybe to do the transition, I would like to ask you another question, Prof. Kim. There is an issue that you have not discussed much during your presentation, and I hear a lot about it in the machine learning community. It's the idea of physics-aware and physics-informed machine learning. In other words, beside the data and the artificial intelligence, what do we do with the expertise and the knowledge of the researchers, the engineers, and the professionals? So how do we inject in the equation that you are showing to us the knowledge, the human knowledge?
That's something I stay away from.
Okay.
It's too difficult.
It's too difficult. So you are not enthusiastic, and you do not believe in the progress that are being advertised at the moment on this on this front?
No.
Okay. Okay.
It's just too big a task, and I prefer to spend my life solving problems I can solve.
Okay. So we have indeed big enough a problem with ABC, and that's a good beginning to work on. So at this point, I would like to pass the floor to Prof. Woong-Kee for the ABC forum, and I would like to ask everyone in the audience to join me before that to thank Prof. Woong-Kee for his presentation. Thank you very much, Prof. Woong-Kee.
Thank you very much.
It was a pleasure to learn from you once again.
Thank you. Hello, I am Woong-Kee, Gachon University, South Korea. This is 2021 first annual World Forum of AI, Big Data, Convergence, ABC for short. The objective of this World ABC Forum is to explore the current status and R&D opportunities and issues in the convergence of AI and big data from a data-centric perspective. This year, we invited 7 world-renowned speakers from both academia and the industry, and organized the World ABC Forum into 2 sessions over 2 days. 4 speakers today and 3 speakers tomorrow. The first speaker today is Professor Jiawei Han. University of Illinois at Urbana-Champaign, USA. And the title of his talk is Mining Hidden Structures from Massive Unstructured Text. Jiawei Han is Michael Aiken Chair Professor in the Department of Computer Science, University of Illinois at Urbana-Champaign. His first authored book, Data Mining, Concepts and Techniques, has been adopted as a data mining textbook worldwide, received over 50,000 citations, and his H-index is 185, ranked among top 5 computer scientists worldwide. He received ACM SIG-KDD Innovation Award 2004, IEEE Computer Society Technical Achievement Award 2005, IEEE Computer Society W. Wallace McDowell Award 2009, and Japan's Funai Achievement Award 2018. He's a fellow of ACM and a fellow of IEEE. We pre-recorded his talk, and I'm going to play the video. Wait a second, please.
I think we don't have the audio shared.
Text.
Oh, it's fine, okay.
So we're living in a big data age. We got massive data coming from everywhere. However, if you look at the real world knowledge, okay, over 80% of real world data actually are unstructured text data, like newspapers, research literature, social media, anywhere. Okay. However, the bottleneck is if we want to use human, sophisticated, substantial annotation training, it may not be scalable. Okay. So what we have been working on is taking massive unstructured text plus knowledge base. We work together to work out embedding. Okay. Then mine structures like phrases, fine-grained entities and the relations, taxonomies, and multi-dimensional cubes, text cubes or classification, a knowledge graph, and information networks. Then we use these structures to mine important knowledge we need. Okay. So let's look at how we are doing something different from the others. Okay. So if you look at the text embedding in 2013, since then, Google actually developed a word-to-vec method. Same thing as Stanford got a Globay, and Facebook got a fast text. Okay. What they are doing is this. We got a massive unstructured text data. We can use one hot vector, but the vector will be really, really long, like hundreds of thousands of dimensions. Such high dimension and sparsity, even we think the documents are back of words, it still cannot reflect the meaning of like a word-word similarity. Okay. However, if we embed this high dimension space into much lower dimension, like hundreds of dimensions, we probably will be able to find something semantically quite close. They will be embedded something closer. Okay. Then if you embed a man and a woman, you draw a vector. Okay. Very likely your king, you get king, you may even using parallelogram to derive where the king's embedding space should be. Okay. That makes things quite promising. Okay. And when we study the similarity, we actually was always thinking about word-word similarity like a cosine similarity, the angles. For example, if we say France and Italy are very close, simply says their cosine similarity is closer to 1, or their theta angle is closer to 0. But if we say boar and crocodile has nothing to do with each other, that simply says their cosine similarity is closer to 0, or their theta angle is closer to 90. If we want to do the calculation, for example, we want to say the embedding of France minus embedding of Paris, but instead of Italy minus Rome, it's in Rome minus Italy. Okay. In that sense, their similarity, cosine similarity, is closer to -1, or you say theta angle is closer to 180 degrees. You can see when we calculate word similarity, we are using spherical space. However, when we do the embedding, we are using Euclidean space. This may not be very compatible. Okay. Then we look at our, another important thing is if you look at the word VAC, okay, the word VAC, you are using their neighboring words, try to find the meaning. For example, if you want to figure out what harmful should be, the meaning, you look at a plus minus 5, you try to figure out what's the meaning of harmful. However, in this text, you clearly see plus and minus 5, you will not be able to get a hint on what should be harmful. However, if you go a little stretch, a little long, like the whole paragraph or document, you will find a lot of words. For example, alarm, taunting, shot, danger, rob is something closer to harmful. That means if we want to figure out the meaning of a word, take the center word. One way is we look at surrounding words. Another way is we look at the probability of this word happening or similar words happening in the short document or the paragraph. Okay. In that sense, we are actually thinking about if we want to do embedding, instead of Euclidean space embedding, we can do spherical embedding. Instead of just a local context, we are integrating local and global context. And if we do this, it's easier for us to find similar words surrounding a particular context in the embedding space. Okay. For example, if you look at the, say, acronym, say CMU, if you just look at local context, you may find something which is, not quite meaningful. However, you look at a global context, you will find CMU, you get words like Carnegie Mellon, Pittsburgh, Pennsylvania, Andrew, that actually somehow give you interpretation of CMU. Similarly for other acronyms. Okay. We did some similarity analysis in a pretty big corpus. We compare with WordVac, Global, FastExpert. Those are the Euclidean space embedding, and upon Carey embedding, okay, with our joint spherical embedding, you can see this joint spherical embedding give better similarity in the large context. Then with Jose, with joint embedding, whether we can solve all the problems. Okay. The interesting thing you can see is different applications for different people. They may want to see something to be embedded closer. For example, if you see these 6 names like Richard Feynman and Isaac Newton, if your focus is you try to distinguish politics versus science versus literature, likely Richard Feynman and Isaac Newton could be closer because they were both physicists, scientists. Okay. However, if you say, I'm more interested in distinguishing England versus United States, then Theresa May, William Shakespeare, and Isaac Newton should be embedded closer because they were all from England. You can see different people have different thinking, different applications. They may want to generate different kinds of embedding. That one, we call this one is category name guided embedding. Now we look at a little math to see how we really compute this. Okay. You look at these several probability multiplication, you may think it's pretty complicated. Actually, if you really think about this, okay, this C is category. This D is your corpus. You want to partition your data, somehow compute surrounding your category. How do you do that? you can see there are 3 multiplications. Okay, one is you look at your word wi, and you look at plus minus k, and here is essentially plus minus h. That space, that one essentially is very much like a word vec. Okay. Then you look at this D, this WI, the probability in this document. This is very much like our global embedding, or you can think about this one is very close to latent deletion topic modeling, latent deletion application. Okay. Then the first one essentially is this category, this document in this category versus this document under the condition of this category. These 3 essentially give you embedding using something like a word-to-vec idea, and within the documents distribution and within category distribution. If we calculate this using, say, clustering idea like EM algorithm, we actually will get something semantically quite close to be clustered together. Okay, so you can see what we'll get. Okay. We took the experiments is we take New York Times, pretty big corpus, okay, and people may think they want to embed something according to location or according to topic. Let's look at this. If you take New York Times, you say I want to distinguish Britain versus Canada. Okay, you probably can see under Canada you get Ontario, Toronto, Quebec, Montreal, and Ottawa. Those are our most important Canadian provinces and cities. Okay. However, if you use latent deletion application, typical topic modeling idea, you probably can get something, but barely they are really that sharp. Okay. Similar thing you can see if you want to distinguish education versus politics. Or in Europe, you want to distinguish different kind of food or different kind of sentiment. You probably can see we can automatically generate something pretty distinctive. We call this one is discriminative topic mining. We actually did a quantitative study on topic coherence and mean accuracy. You probably can see on location, on topic, on food, on sentiment, the Kate category guided embedding Kate actually can give you a very good measure. Okay. Now, we actually did this in the real data sets, for example, 2019 Hong Kong protests. Okay. And within this protest, we actually partitioned this category into politics, police, economy, information, infrastructure. Of course, some words probably too abstract, like infrastructure. Then we need to give a few seats, like we give 3 seats, Hong Kong University, Transportation, International Airport. Then those black ones, black ink words, actually are generated automatically based on large corpus. You can see it's pretty sharp. For example, under police, you see water cannon, pepper spray, petrol bomb, in backgrounds, and firing tear gas. Okay. Then you look at the information, you can see there are Chinese state media, BBC News, Global Times, Sina Weibo, and internet censorship. Okay. So even we can do this in a hierarchical way. For example, we work out a joint spherical tree and the text embedding together. Okay. That means not only we look at one level, like sports, arts, and sciences. Under sciences, we actually look at biology, physics, and chemistry. Okay. And with this, you can see using spherical embedding, you may get something pretty sharp. For example, under arts, we generate theater, artist, contemporary, classics, and studio. Then you go down to the hierarchy under music. You see we can generate sounds, tunes, guitar, melody, and jazz. Okay. So that means you really can automatically plug in to find in-depth discriminant topics. We actually tried for the PubMed literature on the COVID-19 study. You can see we actually can go down to hormones, enzymes, vitamins, and vaccines. Generally, all those words, very distinctive and dedicated to one category. With this, we actually will be interested in whether we can use such philosophy for document classification. We know document classification traditionally people needs a lot of training data. However, we try to use weakly supervised text classification. That means we give very few labor data. Where does labor data come from? It can come from labor surface names like politics versus sports versus technology. Or you can get a few class-related keywords for each class. Or we can get a bunch of documents they are labeled in each class. With this, they are pretty weak in the sense it's a very small number of labels. Then we go into a pseudo document generator using embedding, using the pseudo document generation. We generate these documents, then we plow through, we feed them into deep neural networks like CNN or RNN as a pre-training. Then using this pre-trained neural network model, we can do pretty good quality text classification. However, we found if we can use pre-trained language model, we can even do better. Okay, that means we can use a language model to do self-training. For example, okay, if we just use labor name like politics versus sports versus business versus technology, the pre-trained language model like a bird can generate lots of vocabulary in each class using discriminative topic mining. Okay. However, not a single word is distinctly enough. We actually have to rely on the context. For example, if you look at this sentence, this one said the oldest annual U.S. team sports competition. Then they list a bunch of sports. Okay. So that sports really mean like baseball, football, soccer. Okay. However, you look at the second sentence, Samsung's new this mobile phone sports a built-in hard drive can store a lot of data. Okay, that sports actually means featured. Okay, so you probably can see they are very different. However, if you use a language model prediction using masked language model, you actually can see based on the context they generate very different, words. That means the first one is really about sports. The second one is more about features. Using this masked topic prediction together with the self-training, we actually can get a very good classification algorithm called lot classes. It means labor-only text classification. With this, you can see in the pretty large data sets, compared to other weakly supervised classification, and our method is far better, with far better accuracy compared to the others. Okay. Of course, comparing with fully supervised classification, we still have some distance. That means you get much more labor data for classes, for documents. You still can get something better. However, we did the study, we actually found our method, large class method, actually one label, one class label, okay, actually equivalent to almost BERT fully supervised version 48 labels. So that means actually in the real life, people may have a burden to give you so many classes. This could be very effective. Okay. Then with this, actually, the people like Microsoft Research actually give our student Jiaming Shen a very challenging task. Say you can do labor-only classification. Now we give you some real test. Okay, we have scientific papers like in Microsoft Academic Graph. Then they have a big hierarchy. They want your paper to put a set of relevant class. That means multi-class classification. For how many classes? They have 25,000 candidate classes. Similarly, for Amazon reviews, you can see they have 15,000 candidate classes. How can we get a multi-label tagging for such a huge number of classes? Okay. So we found, if we take the 25,000 classes as flat date classes, it becomes really hard to find out which class is the best match. However, those different classes actually they naturally arrange in the hierarchy. And usually people like any like a Microsoft Academic Graph or Amazon, they can give you a hierarchy of their classes. Okay. With such hierarchy, you start from top going down. It becomes much easier. For example, look at this document. If you say, now at the top level, we need to classify this document, whether it's about information retrieval, about computer theory, about data mining, about computer architecture. That may become an easy task because you just look at the keywords and the document classification. You may be easily recognize this one is about information retrieval. Then you can go down, okay? And for each one you go down, you go to next level, they may have 10 to 20 candidate classes. Sometimes you may say, I cannot clearly decide that you can have 2 active points, then you can go down. And finally, if you can find the most closest classes matching this document, we call this one as core classes. Once we can find these core classes, things become much easier. So let's look at how we do this. Okay. That means we search top-down exploration, and we may find more than one candidate at each level. Okay. And for each level we go down, we may find a bunch of candidates. However, if you look at this going down, you may find which one is the closest one match this context. Okay. That means if you go down this, you may find that this document match information retrieval is about 0.7. However, match SVM rank is about 0.9. Then you can look at it for SVM rank, its 3 relevant classes. This document actually ranked it the highest one. So in that sense, we will say this document's core class is SVM rank. Okay. And once we can find the core classes, we can go back to search these, usually their parents, core class, their parents, could be very good tags. For example, if you look at this one is a crafted cereal and baby cereal. Okay, if you look at this whole rare document, they don't really have a baby. However, with embedding, you can easily find our son was about 4 months old. That one itself actually implies it's baby, right? So you get these two, then you look at its parents like a baby food, or even its grandparents like a baby product, could be reasonably good classes. Okay, that's where we can get a multi-class tagging. Okay, and with this method, we compare with many other methods, including some semi-supervised or some pretty, give lots of class label or zero shot. These kind of methods, you can see the text of class based on taxonomy, top down to go down to find the class labels, give you far better F1 value and precision at 1 value. Even we are facing pretty large number of classes. Okay. So here I just give you a few interesting examples in our recent study. The general philosophy is we want to do structured mining of massive text data. We get unstructured text, we have knowledge base, we try not to use massive human annotation or supervision, but we can do phrase mining, fine-grained entity recognition, Then we go down to generate a multifaceted taxonomy, multi-dimensional classification, and knowledge graphs. With such structured help, we will be ready to find recognizable, actionable knowledge. Okay. In our past many years, we have a good evolution path. We start from data mining, gradually go to link mining, mining heterogeneous information networks, mining latent structures. In recent years, we actually gradually getting into mining structures of factual knowledge from text, and phrase mining, and multi-dimensional mining of massive text. Many of these students, they got a PhD, their dissertation, received the award. Okay. And currently, all these become university professors or industry lab major researchers. Okay. So my talk using these several recently published papers, I should say, like Jiaming's paper on the hierarchy classification, taxonomy-based classification. He actually joined Google Research this year. Yimang actually received the 2021 Google PhD Fellowship, and Jiaxin Huang, she received the 2021 Microsoft Research Fellowship. Okay. So we also get abundant support from federal agencies and industry research centers. So thank you. I would love to receive your comments and questions. Thank you.
If you have any questions, please turn on the microphone and ask questions. Professor Jiawei Han is here, and he will live answer the questions. Professor Han, I would like to ask 2 questions.
Yes, please. Okay, can you hear me?
Yeah.
Okay, that's good. Yeah, just go ahead, please.
Yeah. On page 25 of your presentation, the example F1 value for Amazon data was much lower than that for DBPR data. Could you please explain what caused the difference?
Yeah, so actually you probably can see this, okay. In many text mining or natural language processing, so there are 2 challenges. One challenge actually is, you probably see the recall, is there are lots of articles or text related to the question, and by retrieval or something, you may miss quite a lot. So that's the one you get a lower recall, okay? Another one is where you get this one, how you precisely identify, the one which exactly relate to your question. That's actually the precision problem. So for text understanding, there are many questions. The reason is you not like human. Human got trained, you have lots of knowledge, you have lots of background. But for computers, okay, you actually just based on what you have. For example, you are given one article or one sentence, you may or may not be able to link to the very large knowledge base right on the fly. So there are still lots of challenges. That's exactly, for me, in the past, I first worked on structured data mining. Then I find the major challenge actually is on the massive text, how to really understand this. Okay, so the recent deep learning, especially pre-trained language model, they are trained using very large corpus, very large, you can say, knowledge base, or even unlabeled, unsupervised but a massive amount of human, communication data. That can help a lot. That's why recent study on the text mining actually got lots of progress around this pre-trained language models. Thank you.
I would like to ask one more question. When we are going to choose the target of massive text mining, which should we focus more on between the data with lower example F1 or the data with high example F1 value?
Oh, okay. So that's actually a little tough question. The reason is, in my view, okay, when you do text mining, the most important thing is try to get massive unlabeled data. The reason is this: of course, you may get some label which can help you, but on the other hand, the label always will be limited. No matter how much you ask human to do annotation, it's still limited. But if you get a massive unlabeled data, once you get almost like all the surrounding data sets or text, it will help a lot. So in my research, my group, actually, we do not care that much on the initial one you give us, whether it's a very high F1 or very low F1. We actually want you to give us as much data relevant to the problem as possible. Okay, so we rely on the massive unlabeled data, try to derive things. You probably can see our like a cage. We actually only ask you to give very small number of labels, but you need to give us a pretty large corpus in order for us to function well. Okay, overly.
Okay.
Yeah, thank you.
Thank you very much. Is there any questions? Professor Jiawei, thank you for your kind answers for the questions.
Yes, you're welcome. Yeah, so anybody who wants to communicate with me on more questions, feel free to send me emails. Okay, thank you very much.
Thank you. Thank you very much.
Thanks, bye.
We are going to proceed to our second speaker. The second speaker is Professor Jaideep Srivastava, University of Minnesota, USA. And the title of his talk is Deep Knowledge from Shallow Data, Machine Learning on Wearable Data for Medical Insights into Chronic Conditions. Jaideep Srivastava directs a laboratory focusing on research in applied machine learning, focused in the areas of social media and health informatics. He is a fellow of the IEEE, has been an IEEE Distinguished Visitor, and has been awarded the Distinguished Research Contributions Award of the PAKDD for his lifetime contributions to the field of machine learning and data mining. I'll play his presentation video. Wait a second, please.
Hello, welcome to this presentation. My name is Jaideep Srivastava, and I'm from the University of Minnesota. And I will be talking about the application of machine learning from body wearables for medical insights. And we'll be applying it to a number of different cases. So here's the outline of my talk. I will first talk about the potential of wearable devices, and then go into 3 specific cases. That is, a diagnosis case for sleep medicine, and second is therapy management again in the area of sleep medicine, and finally, a triaging example for ICU patient management, which is intensive care units. Okay. So here is a diagram. I've drawn it like a 2x2, where the x-axis shows that the fidelity of information, that is how detailed an information is available, and y-axis is about ubiquity. That means, and that ubiquity has two dimensions, that is whether it is available all the time, and second is all of the people. And you could say that on the top right is something like a pacemaker, that for the few people that do have pacemakers, it gives you very detailed information, and therefore the highest possible fidelity and all the time. Now, if you look at the right bottom, you have something like a polysomnography, which is that someone goes to a sleep lab and they sleep over there, and they have all these sensors available, and data is collected about them. And then if you look at the top left, you have something like wearable devices. The disadvantage is the data is of lower fidelity, but the big advantage is that those are available to lots and lots of people. Okay, so what is the impact of all of this? The key issue is of my research is how can deep advanced analytics, like deep machine learning, for example, extract medical value and medical information from wearable data. So here is a picture of how the thinking of the doctors themselves, the medical community, as well as, of course, the whole field is changing, moving from what is called episodic care to continuous care. So what is episodic care? Episodic care is that the patient visits the hospital periodically, because there's a test that is done, there's a follow-up, and so on. And the doctors and the whole medical community gets to see what is happening with the patient periodically. But they don't know what is happening in between. And therefore, there are these episodic interactions, one episode at a time, and that is based on that is how the care management happens. What do these wearable devices do? They actually fill in this gap. So from smartphones to smartwatches and so on, they are providing not as deep an information as you would be collected on a medical, a visit to a hospital or a clinic, but they have the advantage of providing continuous information. So what is happening is that the doctors can have a more detailed view of someone's life, because in addition to the episodic data that they collect, they also have this continuous data being collected. So what does this do for us? So let's see first how it can help with something like diagnosis. So here's a particular problem that sleep disorders, supposing someone is not sleeping properly and they feel that they have some kind of a condition, or when they're breathing, all of a sudden they start choking. In fact, that's a classical example of something called OSA, or obstructive sleep apnea, which actually can have serious consequences from choking to even things like heart conditions, because oxygen supply is becoming less. All right. So to do a formal evaluation for that, you have to come to a sleep lab and get all of these things done. Great. So let us say you get it done once. And after that, you're prescribed a particular kind of a device called a CPAP, which is a mask that you wear on your face. And then you can go and sleep, and it keeps on working. And as long as you keep wearing it, you're getting proper, proper kind of sleep, and your sleep apnea can be managed. But the question is that, are you really getting good quality sleep yourself? Okay, so the classical advantage of a sleep apnea device like CPAP is to make sure that your air passageway is not blocked. But the real question is, can you actually get better quality sleep? Okay, so what can we do with this data? So the problem we are going to address is that from the data that is collected from these CPAP devices, can you figure out someone's sleep stages? So for example, here are 4 sleep stages: the wake sleep, REM sleep, light sleep, and deep sleep. And medically, this is interesting because if you have if you don't get sufficient REM sleep, then there is one kind of problem. If you don't get sufficient deep sleep, there's another kind of problem. Okay, so how can we do this? Now, classically, this has been done a lot from polysomnography. So what we did was we developed some techniques, and here is a data set that we used. It's a well-known publicly available data set called MESA. Okay, and it has many different kinds of data, but the specific one about sleep is 400 sleep apnea patients, 7.5 hours of sleep data per person, and so on. Okay. And the techniques that we have for those, these are the evaluation metrics we used. That is accuracy, percentage of states accurately classified, and Cohen's kappa, the degree of concordance between prediction and ground truth, and then sleep efficiency, mean absolute error. Okay. And here are the results. So there were, if you look at the accuracy measures and then kappa and sleep efficiency, as you can see, that there were some other techniques that had been done before us. Those are shown in the light gray. Things like conditional random field, RCNN, conditional adversarial, attentional RCNN, and so on. And then what we did was we actually came up with a whole class of techniques. As you can see those in the dark gray at the bottom. Basically, neural conditional random fields along with regularization. And as you can see that through a sequence of techniques, we were able to get accuracy all the way up to over 74%. Okay, on the accuracy measure, on the kappa measure, it's a 0.57, and on the sleep efficiency, mean absolute error, under 10%. And what this shows is that there's a potential of looking at a home device and get to almost, if you look at the MAE measure, over 90% accuracy compared to a polysomnography. So this is a significant advantage because this is a significant advancement. Okay, let's move on to something else. Okay, so in this case, as you can see, that this provides a some more discussion on the conclusions. Okay, so the next topic is therapy management, and what is the therapy management problem? So we're going to talk about CPAP therapy churn prediction. What is the problem? We talked about the use of CPAP. One of the problems is the adherence problem. That is, only 60% of people adhere to the treatment. Now, this is a chronic condition, so the CPAP treatment is not a curative treatment. And 40% of the patients abandon the first 6 months. Now, if people abandon therapy, the problem is that the condition is not going to improve. So what is the desired output here is that we want to be able to prioritize the list of patients in respect to the non-adherence prediction, okay, and a more accurate classification and earlier and accurate telemedicine intervention. So what happens right now is that when someone is prescribed a CPAP, they're periodically called in for counseling to see how things are going, if there's a problem, some counseling, and so on. The problem that happens today is that a one-size-fits-all approach is taken. Everyone is invited, everyone is called. And the idea is you really want to be able to focus on those who are not going to adhere, who are going to stop using the device. Okay. So here's a picture that on the x-axis you have time. So the first day, second day, third day, all the way up to 148, 49, 150, 151st, and so on. And what we want to predict on an ongoing continuous basis is whether someone is going to abandon or they're going to adhere. So it's a two-class classification problem, except the prediction is for 6 months down the line. And we want to do it every single day. And this is what we call CTAP, or continuous treatment adherence prediction. Okay. And here is what the results were. So look at the prediction and the average AUC. Clearly, as you can see, that as time goes by, the prediction becomes more and more accurate. And then you can see the baseline is what they use currently. Basically, the current baseline is that if the average usage is more than 4 hours a day, then the person is going to adhere, otherwise they're not. And our techniques are able to do much better than that. And the pink line that you see, the pink broken line, is what is currently used. Okay, and by the way, that is the state of the art in the field of sleep medicine therapy management. Okay, so this, how does this get operationalized then? So the operationalization is something like this. Let us say that we have a whole bunch of patients, okay, and all of these, so let's say there's a patient P1, P2, and so on, and there's a whole big cohort of patients, and all of them have been prescribed the CPAP machine, and they're using them. And every single day, this model runs and does an evaluation of every single patient, and based on where they are in their therapy journey. And what it does is that it evaluates what the risk of non-adherence is. And if the risk is low, it gives it like a green color, says, well, this is fine. Just maybe send them a message, right? Congratulating them for using it and so on. Or you can, if it's a medium risk of non-adherence, that means of quitting, then you maybe call them, contact them through telemedicine, or if they're at high risk, you might go ahead and invite them and reach out to them and say what is going on. Okay, so this is an example of how it would be put to use. The last one is on ICU patient management. In this particular case, what we're saying is that the problem is something like this, that now you have, let us say there's a patient who is in the ICU, okay, and data is being collected by time series signals about them, and so that is like instrumentation data, and there's of course their EHR data from things like blood tests and so on, and other information, and then also there is doctor's notes. The idea is, how can we combine all these three kinds of data? That means the continuous data that is coming from medical instrumentation, the lab data like pathology and so on, which is episodic, and things like doctor's notes, which is text data. And from all of that, how can we do better acute care and cost management? Okay, so there are different kinds of things that have been done. Problems like in hospital mortality, decompensation, length of stay forecasting. We will focus on decompensation, which is how a patient is deteriorating. Okay, and these are a couple of different kinds of models that were built. I will not go into the models. Let us look at some of the baselines and finally some of the results. These are actually some of the results that were done at a working hospital, and in fact this was done for COVID-19 ICU patients. And as you can see in our model, we were making three kinds of predictions: 7 days ahead, 72 hours ahead, and 48 hours ahead. And in fact, we made many others as well, but these are the three that we're presenting here. Now, what we're trying to predict is, so for example, let's look at the 7 days ahead model. What it is saying is that 7 days in advance, we're trying to predict if a person is going to die or if a person is going to survive. Okay, and now deaths is obviously very conservative. If we predict that someone is going to die, only 1 out of 4 is actually dying. Okay, so that's not bad, because the others may, other 3 out of 4, they are kind of surviving, but they probably are in a bad shape. On the other hand, when we predict that someone is going to survive, that prediction is over 97%. And in fact, for 48 hours, 72 hours ahead, it's like over 98%. That is good news, because what you can do from this is that pay attention to those who are really sick and pay more attention to them, and pay less attention to those who are less sick. Okay, so that's sort of the whole idea. Now, right now, what is happening? Right now, what happens is that the doctors look at a patient and on the spot make a decision as to whether someone should go to the ICU or not. Or the nurse calls them, or sometimes even the family members might look and say, oh, what is happening to my relative or my friend or my spouse? Okay. And here are some example actual cases. So here's a particular case where a high risk non-ICU patient. So this was a patient that was in the general ward, and they remained in the general ward and eventually died. Okay, and so they never got moved to the ICU. While, as you can see, our models, and there are two models here. One was a deep learning model, one was a logistic regression model, and both of them at a certain point predicted, and this prediction was in advance, by the way, 7 days in advance, okay, that on this particular day, this patient is going to suffer from a serious condition, or the risk is going to become high, so pay attention. So this is a life that could have been saved. Okay. Here's another example. This is an example of a low-risk ICU survivor. Now you see in this picture, the whole gray zone is when this particular person was in the ICU. Now look at our model. We have two risk prediction models, and especially look at the deep learning one, which is the orange one. It says that yes, the risk was high when the person got hospitalized, or rather when they moved from general ward to the ICU. However, very soon the risk went down and remained low throughout, and in the end, the patient survived. If someone had been modeling, using this model like ours, they could have released this patient from the ICU much earlier. What is the advantage? The advantage is that then the ICU becomes available for someone else. And as we know, especially for COVID patients, ICU beds, ventilators, and so on have become the most critical resource, especially when the peak arrives. Okay. So here's an example operationalization of the model. That means you can give a certain risk score, and then based on risk, you can make all these different decisions. Okay. In fact, right now, we're in the process of operationalizing this and testing this out in one of the hospitals out here in Minneapolis. So what we did was we actually took real data and said, well, let us simulate a policy like this. Okay. And what this shows is that by using all these different kinds of models, in how many cases you could have delayed the admission, or how many cases you could have done early discharge. So this shows that a huge amount of resources could have been saved. Okay. So come back to this picture, that potential of wearable devices is high. And the key thing is, how can we use deep advanced analytics to extract value from wearables data? And that is what makes it really useful. The key thing is that we are now in an era where we can move from episodic care to continuous care, and that is the real promise. Okay, and I gave you hopefully some examples of, one is from diagnosis side for sleep, and the one is therapy management in the case of chronic conditions, and finally in an ICU triaging situation, it wasn't quite wearables, but what it was how, again, continuous data can be combined with episodic data to come to better decision making. Thank you. And now I'm open to questions.
If you have any questions, please turn on the microphone and ask questions.
Hello, I'm here live. So if anyone has any questions.
Professor Srivastava, I'd like to ask one question. Some people with sleep apnea may not want to disclose their medical data. On page 10, you showed several methods for sleep state classification. Can these methods be run on a smartwatch or a home computer?
Right. Yes. So I think to your first part, I think what we have noticed is that the patients don't seem to be as concerned about this issue of privacy. I mean, I guess clearly there's a opt-in, opt-out about it, and as you know, in the US, privacy laws, especially medical privacy laws, are fairly strict. So if someone doesn't want to do that, obviously it won't. But at the same time, people who are suffering from serious conditions, they seem to be okay because the results of all of these are only going to be known to their doctors and not anyone else. So clearly the data itself, of course, is collected from the device and then goes to the device manufacturers, but actually goes, in the end, it goes to the doctors, and they're the only ones who look at the results. So that is something that is not that much of a problem. But again, at the same time, those who want to opt out of this, they will opt out of it. To your second question, yes, sleep staging has been done also from wearable devices a lot. For example, wrist, smart watches and so on do it regularly. In the case, one of the reasons we were trying to do it from CPAP devices was because the quality that you could do is far better. And then in addition to that, one could do many other things as well. So for example, one of the real promises is that it's also known that if you get more REM sleep, then that helps better memory consolidation. And if you get more deep sleep, then that is actually helps clean some of the chemical deposits that happen sort of neurologically. And in the long run, that is better for like fighting Alzheimer's. And therefore, one of the things that these manufacturers are very interested in is knowing that something like a CPAP device, which largely is for making sure that you don't choke, that it actually has some long-term neurological benefits as well. So therefore, analysis done on this kind of data has benefits beyond just being able to figure out what your different kinds of sleeps are. I see that someone has raised their hands as well. So, Andrea.
Yes, I have a question. First of all, thanks for the very interesting talk on an unfortunately highly pressing issue. I have a question related to the ICU patient management. I found it really fascinating, and I was wondering, did you look into the factors or features that were driving the prediction? Because I would assume this would be highly interesting for medical experts to figure out which clinical parameters are indicative of the survival probability.
That is right. And not only, yes, of course we did. And unfortunately, this being such a short presentation, I could not go into that. And so if you're interested, please contact me. Because yes, we have done analysis of that. And not only that, because we are doing an analysis longitudinally, what we have found is that during a stay over a period of time, the factors actually kept changing a little bit. So what is important is that, for instance, let us say, some particular kind of a thing going up at a certain point may have its impact on something else down the line in about 3 days or 2 days. And those kind of factors, that means, so things that are really, the critical factors that impact mortality, there are some precursors to that happen earlier, and therefore that can be detected as well. So yes, that's exactly the kind of stuff that we're doing. And I'm glad you find this interesting. So please, if you're interested, do contact me.
Thank you. This is really fascinating. Thank you so much.
Yeah. Okay. Any other questions? Yeah. Okay, well then, I guess the only thing I would like to say is that, this whole, the bigger picture in this whole thing is moving from sort of episodic care to continuous care. And that is really the big promise, because after all, the doctors do a pretty amazing job, but remember, they only look at us once in a while, thankfully, while all these, we ourselves live with our body all the time. And if there can be some way of measurement of what is going on in our lifestyle, as well as what is happening to the body in chronic conditions, for example, like diabetes, another big one, then and having some of that synthesized and summarized and sent over to our doctors will help them help us manage our health much better. So thank you.
Yeah, thank you. Thank you very much for your answers and comments. Thank you. The third speaker is Dr. Kyungoh Min, Seegene Incorporated, South Korea. And the title of his talk is AI and Big Data for Molecular Diagnostics, Seegene's Approach. Kyungoh Min is the head of the Institute of Diagnosis Platforms of Seegene, a world leader of molecular diagnostics. He led embedded software engineering teams at Samsung Electronics and LG Electronics. Recently, he joined Seegene to develop AI-based computing system for designing oligonucleotide reagents, which are used for detecting infectious diseases caused by viruses, such as COVID-19. I am going to play his presentation video.
Presentation today is about how computing technologies are used in molecular diagnostics field. During my presentation, there will be several biology-specific terms which may be unfamiliar to many of you. I will explain them as they show up. Before getting into the main presentation, let me spend a minute introducing the company Seegene, where I work. Early this year, Fast Company magazine selected Seegene together with 49 companies, including Moderna and Pfizer BioNTech, as the world's most innovative companies this year. Seegene is a company specialized in molecular diagnostics. Ever since the foundation of the company 21 years ago, the company has focused on developing test kits assays, so to speak, for diagnosing infectious disease using molecular diagnostic techniques. With the breakout of the COVID-19 pandemic since early last year, the company's test kits were suddenly sold out by many governments, propelling it to the leading supplier of the kits in the world. Now, here is what I will talk today. I will first explain what is molecular diagnostics and what is PCR, polymerase chain reaction. PCR has become widely known term thanks to the COVID-19 pandemic. After that, I will explain the design process of reagents for PCR testing. A reagent is a component of a test kit, and it technically means a substance added to a system to test if a chemical reaction happens. In Seegene, computing technologies are heavily used in this design process, which I will explain next. The computer system for reagent design is called in silico platform. In silico here means a process done by means of computer modeling or computer simulation. Seegene's in silico platform and the idea behind it will give you some understanding about how data and AI, artificial intelligence, are in play in developing reagents for diagnosis. I will finish my talk by presenting how Seegene envisions the future world transformed by ubiquitous availability of molecular diagnostics enabled by the technologies developed by the company. So, what is molecular diagnostics in the first place? As the slide says, it is a collection of techniques to analyze biological markers in the genome and proteome. More specifically, it involves detecting existence of a virus in our body by looking for a specific marker such as DNA sequence unique to the target virus. Then, why molecular diagnostics? Molecular diagnostics, MDX for short, has several benefits in diagnosing disease. Among others, it allows early diagnosis of disease by detecting molecular level markers such as DNA, RNA, protein before actual symptoms appear. And because the technique is used outside of a patient body, which we call in vitro diagnostics, it is safer than other techniques which are often performed inside the patient, so-called in vivo diagnostics. Furthermore, PCR technique has much higher accuracy in diagnosing infectious disease than other techniques to do molecular diagnostics. Since Seegene's reagents are used during PCR testing, I will use the next two slides explaining how PCR works and how we design reagents for PCR testing. Essentially, PCR is a technique which amplifies a specific DNA. As this diagram shows, it involves detecting and amplifying a target DNA sequence of a virus, which may be contained in a clinical specimen. In other words, a piece of tissue taken for analysis from a patient. Simply, a PCR is a technique which does amplification of a specific DNA. So how does it work? PCR was invented by an American biochemist, Carey in 1993. It involves 3 steps of manipulating DNA sequence. A DNA molecule is in 2 strands of DNA sequence which are traced together. The basic idea is to utilize the property of DNA sequence with respect to changing temperature of its environment. When a molecule is placed in a high temperature, the strand pair separates from each other. And when 2 strands are placed in a low temperature, each strand attaches back with another DNA sequence. The separation of 2 strands is called denaturation, and attachment of 2 strands is called annealing. Also, in this diagram, the generation of the remainder of the new strand is called elongation. Another property of DNA sequence is that when 2 strands is about to attach each other, because of chemical property, only a specific pair of DNA sequence may attach each other. Among 4 nucleic acids in a DNA strand, which we often call base, ATCG, or adenine, thymine, cytosine, and guanine, which are basic elements of DNA sequence, only 2 specific pairing may happen. That is only between adenine and thymine, and between cytosine and guanine. Hence, in order to detect the existence of a particular virus, we make a specific DNA sequence that attach a particular DNA subsequence of a target during the annealing phase. This specific DNA sequence is called primer. A primer is a DNA strand of short length, between 5 to 30. It is called oligonucleotide, or oligo for short. In this diagram, there are 2 primers colored red, which are attached to each separated strand of the target DNA sequence. After the annealing step, an enzyme is used to expand it to the full length of the original strand of DNA sequence. This phase is called elongation phase in this diagram. This enzyme is called polymerase, hence comes the name PCR, polymerase chain reaction. Repeating this 3-step cycle, each cycle doubles the number of target strands. The target DNA strand is amplified to the extent that we can detect its existence in the specimen. Now, let me explain the whole reagent development process. The whole process is made of 6 steps. The first step is target selection step. In this step, you select the pathogen you want to amplify. Pathogen means an organism, that is a virus that causes disease. After such selection, the next step is to collect all the target sequence, in other words, mutations for that particular pathogen. This collection of data occurs almost daily in Seegene, and for a particular variant of COVID-19 virus, for example, it amounts to almost several terabytes of data nowadays. Next step is to find the conserved sequence or conserved regions, which means identical or similar DNA subsequence across all mutations of the virus. After such discovery step, now you develop a single set of primers that can detect a single target. In this diagram, a single oligo set means a set of primers for detecting a single target. Recall the earlier explanation where 2 primers are needed to do the amplification. Afterward, the next step is to develop a multiplex reagents that can detect multiple targets during the using the sets we found in the previous set. Normally, in order to reduce the time to detect existence of target virus, a test is done to detect a few viruses in one experiment. Thus, single oligo design step is repeated against other types of viruses, and eventually we come up with a number of such sets. Finally, in the last step, clinical trials are performed to check if it does indeed detect the target virus. Among these 6 steps, let me show you in the next 2 slides how computing technologies are in play. Here is a diagram of what happens during the 3rd step, the conservation region search step. For all COVID-19 virus sequence we collected, we align them together and look for a highly conserved region. Just to give you a flavor of computation needed to do this search, nowadays, for COVID-19 case, we have to do this alignment among 6 million sequences. Since there are slight mutations such as modification, deletion, and addition of DNAs among the same pathogen, we need to align them all and look for common region of DNA sequence, which is very much compute-intensive task. Here is what to consider in designing primers for detecting a single virus. Essentially, out of the conservation region found in the previous step, we narrow the target region of 300 or so long DNA subsequence, and we design primers that attach with each end of the target subsequence during the annealing phase. Here we listed 4 factors when determining the region and the primers: sensitivity, dimerization, specificity, and efficiency. I wouldn't spend time on explaining what each of those are. In this diagram, we show yet another primer of black color in the middle. This is an oligo which is used to emit light when it is annealed to the target. This light emitting mechanism is used to detect the existence of virus. Hence, for each target detection, in this PCR method, basically 3 primers are needed. The 5th step is about designing reagents that can detect a number of pathogens simultaneously. In diagnostics, it is important to be able to run the test and quickly decide if there is any virus. Many possible combinations of primers are found, and among those candidates, we need to select the best ones. Since these primers could anneal among themselves during the test instead of the target pathogens, we need to design a few alternative sets of primers for a single pathogen. When a primer is attached to an unwanted target DNA sequence, Such annealing is called dimerization. This unwanted dimerization could happen in the test tube, since we often end up having tens of, sometimes hundreds of primers together in one bottle because of the multiplexing need. How to select best primer combinations? This selection process incorporates many design parameters, and we are trying to adopt machine learning technique based upon the many actual experimental test results collected over the years as the input data. Shown in this diagram, Seegene has a unique design method which enables the largest number of multiplexing capabilities in the industry. Because of that, Seegene's kits enable much faster detection of virus. Now, as the last step in reagents design, actual clinical trials are performed in order to confirm its performance. When such trials prove successful outcome, applications for licensing are submitted to government agencies for final approval. Nowadays, in Seegene, reagents are designed based on computerized technologies which embody a number of software techniques and primer design know-how accumulated over the years. Until 2015, designs are done in traditional way, essentially trial and error and lots of manual processing. Since 2018, the company began to use computing technologies to automate the design process. Years of reagent design experiences for obtaining the optimal set of primers has been translated into software algorithms. The title of this slide is Developing Syndromic Assay Products. Syndromic means the capability of simultaneously testing multiple pathogens. Syndromic assay products means products which enable such multiplex tests. Over 14 years, areas of know-how were translated into 895 design parameters. These parameters are embedded in the artificial intelligence algorithm portion of SGDDS, Seegene Digitalized Development System. We are almost at the point such that once a person has come up with an idea about a reagent for a set of infectious disease, he may simply feed that data to SGDDS. Then SGDDS will generate a number of design protocols which provide the optimal set of primers, among other things. Hence, based upon the SGDDS generated output, it can simply make the actual primers and, after collecting clinical samples, conduct the evaluation of the reagents. We expect the application of molecular diagnostics can be extended to non-human disease. Until now, reagents development is confined to dealing with human disease. But Seegene's in silico platform will broaden the application of this way of diagnostics for diverse areas such as plants, fishes, foods, etc. We are striving to making this vision realized by providing our in silico platform available to many outside biology researchers and medical professionals and inviting them to join us in developing reagents that can be used to diagnose many infectious diseases, which has been almost unthinkable until now. Finally, Seegene believes early detection of any disease help make treatment much easier and even enable prevention of any widespread pandemic of the infectious disease. We believe when people take advantage of molecular diagnostics in everyday life, it would become a critical driver to revolutionizing the existing healthcare market. Thank you.
Is Dr. Kyungoh in here? Yeah, he's here. Is there any questions?
Could you open my request, the video? I just opened it. Can you hear me?
Yeah. Dr. Selfinga, could you please give Dr. Min co-host authority?
If the audience could hear my voice, I'm open for any questions.
Yes, we can hear you, and you have co-host permissions already. We can also see you.
Okay.
Okay, thank you.
Well, maybe I could start with a question. So first of all, thanks for the interesting talk, and maybe from the impression of the breaking news from the weekend, I think everybody is wondering about this new SARS-CoV-2 variant, the Omicron. And so based on the platform that you presented, I'm actually wondering how long does it take to adapt this platform towards such a new variant? Is this easily accomplishable, or do you need a longer time scale, and how is the effort? So maybe you could give us an indication on that, please.
Okay, yes. Actually, at the moment, the company is very much busy preparing for this, the new test kits for this, identifying the Omicron, the new variants. And actually, the problem is, during my talk, I already described how we design our regions. The problem is the current Omicron variants, we only have about 140 incidents of mutations. So it is too few. So it is still not clear whether we have enough data to actually design the primers to detect this virus. However, we already have some our own test kits, which already designed for some of the genes that's contained in this new Omicron mutations, because they have the same mutation in earlier variants. So we are trying to talk to government agencies to so that they could try use our already developed test kits. However, for these new variants, we have not enough number of variants to actually make sure that our we could start our own test kit development for that variants. I hope it will answer your questions.
Yes, thank you. That's interesting.
Yeah, so we only have about 120, 140 incidents of this mutations so far worldwide right now.
Yes, but I'm a little confused because these are sequenced. So the sequence alone is not enough. So can't you synthetically synthesize the sequence and start from that, or do you really need probes of infected people for building your test kit?
So what happens is when there is any discovery of a new variants, they all report it to worldwide database, mm-hmm. From which we collect all these variants of all these mutations. From there, we design our test kits. So I wonder, if I answer your question correctly, but then, the way we design our kits is we first need to collect all the actual incidents and which, it should be reported wherever, that actual, discovery happens.
Mm-hmm. Okay, thank you. Thank you very much.
Okay. Any other questions?
I'll ask a question.
Okay.
Thank you for your talk. The topic is particularly timely, I think. Would you tell us about the size of the typical data sets used in reagent development and typical computing time?
Data set means, there are many different kinds of data sets. And as I said earlier, when we, for example, for delta variance, for example, the data set that we download from all over the world amounts to about 2 to 3 terabytes of data. But then, however, from there, we reduce the data to in order to align them so that we could find the conservation regions. So there is one particular instance of the data set size. And when we do this conservation region search, the time to actually determine the region depends upon how you design your actual computing systems. However, in our company, we have about 16 machines, each of which has about 16 cores, and we do the parallel, processing of this region search. Oftentimes, it takes several hours, 7 to 8 hours, and so we are trying various ways to, shorten this search time. Just give you some rough idea about how it will take.
I would like to ask one more question. You mentioned that the Seegene development platform uses AI technologies. Specifically, what are they, and for what purpose are they used?
So, as I said during my talk, we have lots of parameters, about 890 parameters that's already included in our in silico platform. And this is, I would say, kind of an old-fashioned expert system kind of AI. But then the oligo design that comes out of this system is not perfect. So we have to include lots of trial and errors afterward. So what we are now trying to do is we are trying to incorporate the test actual experiment output into kind of doing some kind of a machine learning ideas to incorporate it. However, it is still kind of early, so we need to collect a lot more experiment data in order to incorporate this machine learning designs into our system. So our in silico platform is largely based upon tons of design rules that we developed with our biology scientists. Okay.
Dr. Min, thank you for your answers.
Okay.
The last speaker today is Professor Michael J. Carey, University of California at Irvine, USA. And the title of his talk is AsterixDB Meets Machine Learning. Michael J. Carey is a Brand Professor of Information and Computer Sciences and Distinguished Professor of Computer Science at UC Irvine, where he leads the AsterixDB project, as well as a consulting architect at Couchbase Incorporated. He spent a dozen years at the University of Wisconsin-Madison, 5 years at the IBM Almaden Research Center, working on object relational databases. He is an ACM Fellow, an I3 Fellow, a member of the National Academy of Engineering, and a recipient of the ACM SIGMAT EF Code Innovations Award. His current interests center around data-intensive computing and scalable data management. I'm going to play his presentation video.
Hi, welcome to my talk on AsterixDB Meets Machine Learning. I'm Mike Carey, and this is joint work with my staff member Ian Maxon and recent PhD graduate Gift Sinthong at UC Irvine. All right, so what I'm going to be talking about is kind of summarized here. I'll give you a brief intro to what this talk is. I'll talk about Apache AsterixDB, which is a big data management platform. And then I'll talk about sort of two sub-projects. One is called A-Frame, and the other is support for Python UDFs and AsterixDB. So A-Frame and Polyframe are intended to make big data feel small, and our support for Python UDFs is designed to enrich the query experience in ways that I'll show you. And then I'll summarize, and then I'll take live questions. Okay, so AsterixDB is basically kind of the underpinnings, and machine learning is the rocket science. And so what we want to be able to do is sort of launch the rockets using our data management platform. Okay, so AsterixDB itself is about a dozen years old as a project. It's sort of a one-size-fits-a-bunch project, which was in reaction to the, sort of the one-size-fits-all era is over and you need many specialized systems. We believe that one system can serve quite a few needs. This is joint work between UC Irvine and UC Riverside. And basically what we've done is to take ideas from parallel database systems, from the database community, from first generation big data systems, from the distributed systems community, and semi-structured data management, again, from the database community, but for dealing with flexible data, and to build a system that I'll show you a little bit about, and then to use it in the ways that we'll be talking about here. We developed a bunch of wishes, essentially, the ability to manage data, not just to analyze it, but we actually store and manage data. We have a flexible data model. We have a full query capability over that data, and you'll see as we go. One thing I want to get across is what do we mean in the AsterixDB world by big data? What we mean is data that does not fit in memory. You can scale out your cluster and have a whole bunch of nodes, but it would still not fit in memory. And the reason is it wouldn't be cost effective necessarily to buy enough hardware to keep everything that you need in memory. That just doesn't, make financial sense. All right, so let's start with Apache AsterixDB. So let's talk about sort of the launchpad, right? So it's based on a data model we call ADM, the Asterix data model, which is an extension essentially of JSON, right? So it's JSON++, if you will. And this is an example of, sort of a hypothetical sort of new, web service we want to build called Tiny Social, which is kind of like Facebook meets LinkedIn. And so we're going to have users. The website's going to be called Gleanbook. And so we're going to have users which have things like an ID, an alias, a name, when they joined, and then they can have friends, right? So we can have a multi-set of integers to represent sort of the links to the other friends. And then we could also have the employment history because it's, sort of Facebook meets LinkedIn, if you will, the employment history for our users. And the employment history would be an array of records that capture who they worked for, when they started, and if they're not still there, when did they end? Okay, so this is an example of the sort of more rich kind of data type that you can use in AsterixDB. And then you can create a data set of that data type to store instances of it. Now, AsterixDB has a flexible data model, right? So it's based on extending JSON. It's got rich types. You can support spatial, temporal, textual, as well as sort of usual record kinds of data. For representing data, it has records, lists, and bags as constructors, and it has an open as opposed to closed typing system. So this is what you'll find in an instance of a user in a data set that's declared to be of that type, but you can also have other information about the user. So this is kind of the lower bound on the information content that's required to be stored in this data set. And in fact, you can be very flexible. You can have no sort of predefined information at all except your primary key. And so we could have equally well defined Gleanbook users in this way, saying they have an ID, which is an integer, and the rest is TBD. We could create the same data set from that and store the same information. Actually, we could store more flexible information this way, right? So the nice thing about having a data type is it tells you a little bit more about what's going to be in that data set. Here's another data type we might want to have in our Facebook meets LinkedIn kind of scenario. So we're going to have messages, right? So people can send each other messages. And so we'll have a message ID, an author for the message. Possibly it's in response to some message. Maybe the sender location will be recorded. So we have an optional point. We also support geometric types. And then the message itself. And so we can create a second data set, Gleanbook messages, to contain those, right? So we have users and we have messages, and that's going to be our little toy example of a database to talk about. All right, so what about queries? So for queries, basically, we have an extension of SQL, which we call SQL++, the extension. And so this is just an example to get across the flavor of the language to you. So this example will list the usernames and the messages sent by Gleambook social network users with less than 3 friends. Kind of sad, right? But so what this does is get the username, then it uses a subquery here to select the messages that correlate to that user. And it's basically selecting sort of the whole message from users, and then it's saying where the number of friends, the collection count, the number of entries in the friend IDs collection is less than 3. So that's an example of the kind of thing that you can write in that language. And this is the kind of results you might get back. And so here we have sort of the username, and here we have the messages, right? So we're selecting the message part of the messages. Highlights of SQL++, the language was designed by Yannis Papakonstantinou at UC San Diego, and you can read more about it in the AsterixDB docs or a book by Don Chamberlain, father of SQL, that describes SQL++. Okay. All right, under the hood, AsterixDB, in addition to having that data model and query language, it's a shared nothing parallel architecture, right? So there's a bunch of nodes that have a runtime system and storage, right, with some number of disks attached. And when something comes in as a query, it gets sort of compiled and then distributed and executed in parallel on the nodes in the cluster. We'll talk a little bit more about this later in the talk, right? And they can have sort of as many of these nodes as you would like. All right, so let's talk about sort of 2 things. Let's start by talking about A-frame, and then let's talk about Python UDFs. Okay, so A-frame is intended to make big data feel small, right? And so that you can work with it like you were working with small data, but in reality, you're working with big data. So how does that work? Well, for a data scientist who's working with small data, they will typically, sort of use Python, pandas, and we'll do it maybe on their laptop, right? And then they'll take their data, they'll get some results, and maybe they'll do some iteration. They're just working with their small data set that fits in the memory of this machine, right? Big data analysis is a fairly different picture. It's more complex. Data scientists may still start by working in Python, but then when it comes time to get serious, sort of the model has to get handed off to a data engineer who will then sort of code it up, maybe using their favorite, tools, maybe PySpark and MLab. Right, and running this sort of on a cluster, running Spark, right, and feeding it big data and getting the results back. And the problem is, it takes a while, right, for the data scientist to hand off the data engineer, and there's iteration, and maybe there'll be errors when translating from this world into this world, and so it's sort of a cumbersome world. So what we would like is to make it feel more like small data. Right, we'd like big data to be able to be analyzed, but we'd like the data scientist experience to be a small data-like experience. So how does that work? Well, let's first talk about the small data experience. So it's typically based on data frames. Pandas is very popular as a way of working with data if you're a data scientist. And so what is a data frame? It's a data structure, basically a table with labeled axes, has rows and columns, but they're also ordered. It's a programming interface that's based on tabular data manipulation, and data scientists like to use it. Very popular in data science circles. Problems with using pandas to analyze big data is that your data needs to be in memory. Pandas is a single core system. It eagerly materializes results. So at each step of what you're doing, it'll materialize the last thing that you did. And the data representation under the hood is sort of known to be quite inefficient. Okay, so not great for dealing with big data. But let's talk about what pandas does. So here we have a data frame, and we do an operation to, to look at the language of the data frame, right? So we're basically doing what database people would call sort of projection, right? And then we want to find sort of the places where the language equals English. And so this sort of tells us, these are the rows where that's true. And then what we want to do is actually see those rows, right? So then we'll get back basically this sort of projection and selection, actually the selection at this point. And then if we only want to see like the name and the friends count, we can do this operation. These are basically pandas data frame operations. Okay, so those are transformations in pandas. We want to do the same kind of thing, but we want it to work against big data. So A-frame is basically a big data sort of trying to be a pandas lookalike. Okay, so you want to be able to do pandas kinds of operations on A-frames rather than pandas data frames. And what happens is each time you do an operation, that basically is a transformation. At some point, you might do something that requires showing the results to a user, and those are actions. And when that happens, there's a SQL++ query that will get executed against the data in AsterixDB to materialize those results. Right, so here you've got kind of what we looked at before, and at some point you do an action that says, okay, so now what I want to do is I actually want to do .head of 10, and that shows like the 10 of the results, at which point you have to run a query, and it can be a limit 10 query that goes to AsterixDB and gets you back kind of those results. So this is the architecture of A-frame, which allows you to work with data in AsterixDB as though it were not big data, but rather small data, using kind of the same data scientist experience. So what is going on under the hood here is basically, sort of you're going through kind of these same steps. You're incrementally building a query. You're lazily working with the data. So the first query, if you're going to create an A-frame on users, is just going to be sort of getting all the users. And then what that will become is a nested query where now you want to get sort of a language field from the result of that. And then you sort of end up, sort of selecting the value t equals en, so the Boolean, so you get the Boolean vector back, right? And now what we want to do is sort of actually find the entries where the language is English. Again, this is all sort of panda speak up here. And so that will generate this query in SQL++. And now you want to do a projection. And so now we're projecting from that query. So you're incrementally building a query. And at some point, there's a request to see the results. And so you go and run that query now against AsterixDB, and then do the head would translate into, sort of a limit 10 being appended to this query. Polyframe is a generalization of A-frame. So although we in the AsterixDB project can't imagine why someone would want to work with some other system, there are other systems out there and people seem to like them. And so what Polyframe was the idea of making A-frame extensible and basically retargetable to other platforms. MongoDB, Neo4j, Vertica, InfluxDB, some disparate platforms with different, very different query languages and data models. And so the idea was to factor out a set of language rewrite rules and to generalize the database connector so that you could then, sort of take, sort of the idea of a database and say, okay, so, if it's MongoDB, then you're going to have your MongoDB connector, right? And you'll have your MQL, Mongo Query Language Rewrite Rules, right? And so when you say head, that will generate a Mongo aggregation pipeline. So the idea was to make the system extensible so that you could then, write basically a set of rules that describe how to translate from the operations in A-frame into the languages of these disparate backend systems. So that, in a nutshell, is the first part of the talk. Let's move on. That's A-frame and Polyframe. What about Python user-defined functions? So that's something that we support also in our AsterixDB work. And so the idea here is to be able to, sort of use Python functions in your queries, right? So again, what we want to be able to do is sort of to supercharge your queries with Python functions, in particular, ones that perhaps have been learned using machine learning. So our Python user-defined function support enables you, among other things, to take models that you learn using scikit and sort of deploy them against AsterixDB, right? And to do that, what you basically do is you sort of register that model. You write a little wrapper that will wrap the, sort of what's been generated by scikit-learn. You package the results, you upload it to AsterixDB and deploy it. You then bind the SQL++ function that you'd like to be able to use in your queries to that function, like sentiment function, and then you can invoke it like other functions in queries. All right, so this is kind of showing you roughly how little you have to do to make that happen. So you write a little teeny wrapper class, right? You package the result up, you deploy it on AsterixDB, and then you turn around and talk SQL++ to AsterixDB to create a function. In this case, we're creating the get scikit sentiment function, which takes text input and produces a sentiment result. And now you can use that function like any other function in SQL++ queries. So this is sort of illustrating that for you. So this is just showing you that once we've done that you can call that function. So this is going to apply that sentiment function to two phrases. That's gross and this is great. And so when you do that, basically you call that function in a query, and this query is running over that two little constants in this case, just to show you the results. If the text is that's gross, then you have negative sentiment. If the text is this is great, you have positive sentiment. How does this play into queries? Okay, so now I want to be able to use sentiment analysis in my queries, right? So I want to be able to say, okay, I want to get the sentiment, and I want to find, sort of the businesses. I want to select the business information from businesses join reviews where the review has a positive sentiment. So find me businesses, with positive sentiment. And so that runs and gets me back a business. So now I can start using, sort of the sentiment from my machine learn model as a mixed in thing with other predicates in my query. I'm putting a predicate on state, and I'm doing a join predicate, and now I'm saying in sentiment equals 1, and that's computed from invoking the sentiment function on the text of the review. Okay, so you can also use, anywhere that you can put a function in C++, you can use these Python UDFs. And so we could go ahead and sort of say, I want to actually select sentiment and count the number of these, and we'll talk about these in a second, grouped by sentiment. And so basically, I'm sort of looking for businesses that are pizza restaurants, and this is using Yahoo data, and where where the review joins the business ID, and the review day is fairly recent, and so this gets me, in my little example here, what I find is that I have 56 of those with positive sentiment and 41 of those with negative sentiment. So now I'm basically applying sentiment analysis to my businesses in my database. All right, and how does this work under the hood? So under the hood, basically, you have your query. And so this is an example of your query, right? Which is, sort of, let me move my little widget here. It's basically selecting businesses, join reviews, where businesses are in California, and there's a positive sentiment. So we'll take that query and we'll send it in C++, and that query will get sort of compiled and distributed to all the nodes in my cluster. So this is sort of the stuff down here is the runtime system. And then when that executes, it will basically read the data in parallel and come back with the result. Okay, so, and what it'll do in that process is in parallel, will apply that function to all of the data. So it uses, MPP, massively parallel processing, to basically apply these machine learning models mixed in with the other query predicates and so on, in order to enable you to go ahead and use the results of having learned these machine learning models to select data from your big giant base of information. All right, I don't have a lot of time, so let me wrap up. And so in summary, Apache AsterixDB is a horizontally scalable parallel BDMS, big data management system, that has a full-featured querying language based on SQL called C++, and it has an open, flexible data model where you can say as little or as much as you want about the data. And then we talked about sort of two connected projects that use AsterixDB under the hood. One is A-Frame, which is intended to make big data feel small. They can basically interact with their data using sort of the familiar pandas interface, but what's happening lazily under the hood is queries being built and sent to AsterixDB, or in the case of Polyframe, an extension that basically now allows you to send those queries to MongoDB or Neo4j or Postgres, or there's a list of systems that are supported. Okay, and then AsterixDB includes support for Python user-defined functions, which enables you to, sort of do creation of machine learned models, and you can deploy them and use them in queries just like other functions. And then in parallel, they be applied to the data, and so they can be incorporated in your queries and used to get you results where the results of your machine learned models are part of your predicates that are selecting your data. Okay, so that's a very brief whirlwind tour of kind of what we're doing at the boundary of machine learning and databases in the AsterixDB project. And we're under, right? We're basically infrastructure. We leave the machine learning itself to the rocket scientists, and we create the ability to interact with it and to register it in our system. So now I will take your questions in person, as I understand it. So if you want to know more about our project, you can come here, click on this link, and that will take you to the Apache AsterixDB project page. Thanks for listening, and I will stop here.
Is there any questions? Dr. Selfinger.
Thank you for this great talk. So coming from the data science perspective myself, I really love the idea of making big data feel small. So I really would like to applaud these efforts. But one thing that I was actually wondering about, why SQL++? I mean, is this fully compatible syntax-wise to standard SQL, or do people need to learn something new about this language?
Yeah. All right. Yeah, so SQL++ is an extension. It is approximately a superset of SQL. The thing is that in SQL, you have a schema, right, to sort of guide things. And in SQL, you have rules that were basically developed 50 years ago to deal with a world of flat data. So for example, when you have a subquery in a where clause, SQL says, you must be talking about a scalar value. And so I'll check at runtime to make sure you get one row and one column, and I'll unpack it for you. SQL++ has to deal with some of the differences that come when you don't have schema, and also that come when you can have nested data that you would like to manipulate. So it's pretty close to SQL. It's roughly a superset. There is a list of differences, but one of the things I found, so we use this to teach NoSQL in our undergraduate database classes, and so we've literally had thousands of students go from sort of 8 weeks of SQL, and then in week 9 we say, just kidding, no SQL, and we have them use AsterixDB, and the SQL skills, like everything they've learned, ports beautifully, but they have to understand that there are some little differences, like where subqueries come in, like how they're connected to their parent queries. When you say select star, what does star mean if there's no schema? So there are some differences, but they're not major. And then if you click on the link that's showing on the screen, there's a free book. So Don Chamberlain, Father SQL, has consulted with us on SQL++. And he wrote a little book about SQL++, and it's a wonderful book that talks partly about some of the differences and things to watch out for. But to a first approximation, it is SQL, and it has all the SQL goodies these days, including things like roll up and cube and window functions and all of that. So you can apply, if you like to use SQL for data science, everything that could be applied, I think, to SQL++ pretty easily.
Okay, that's great. So it's not a big transition for the standard SQL user. That's fine. So that's amazing. No, yeah. Thank you.
Right. Takes an undergraduate a couple of days.
Okay. So. Good. Thank you.
Yep.
Other questions? I'd like to ask a question. Okay. Thank you for your great talk. It's exciting that you have found a way to map pandas queries to SQL plus queries for big data. I wonder what the limitations of this approach would be. For example, data scientists have to fill in missing data and visualize data in various types of class. Also, pandas and NumPy support various array operations on data.
Yeah, so there's sort of 3 things I guess I would sort of bring up with that. So our focus has largely been on what you might call the relational algebra side of pandas, right? So there's quite a bit of low-hanging fruit there in terms of being able to do the kinds of data manipulations that data scientists do, which are equivalent to relational algebra manipulations. For things like missing data, we do some things with nulls and sort of how we treat those. We actually have a case study paper that's coming out that I could send, if you send me an email, I could send you a pointer to, where we took an Airbnb data science case study that someone had published, and we went through and said, okay, so they gave us their Pandas notebook. It was available publicly, and we took that and we applied sort of that whole series of things to see, could we do the things that they were doing using A-frame. And so there we highlight some of the differences, and there's some examples of where we handle missing data and things along those lines. There's then another dimension, right, which you mentioned about sort of the more sort of vector matrix side of pandas, and there we don't have a great answer at this point, right? So we're dealing with data which is in databases that view data as unordered collections, right? And the data scientists, they do an interesting mix of things. Like when I worked with pandas and first learned it to teach data science, I was sort of stricken or struck by the similarities, yet the differences, right? That sometimes they're meaning, they're doing something tabular, and sometimes they're doing something that's vector-based. And so we sort of struggle a little bit to deal with as do all the scalable data frame approaches, to deal with things like indexed data. And so I think there's still sort of work to be done. And then the third thing is, how do you scale for things like machine learning? So ultimately, these libraries like pandas want to work on data that's in pandas, right? So the pandas, the scikit, library works on pandas data. And so you can use, there's a conversion that you can do to take an A-frame object and, cast it, convert it to being a pandas data frame object. And so you can basically take your large data, do a bunch of things to it, sort of bring it down to a size that's manageable, and then cast it into a pandas object for the purpose of handing it to a pre-existing library that wants pandas data structures, either for visualization or for machine learning. And in that case study, we also kind of looked at that and found that in many cases, by the time you want to visualize something or machine learn something, you've gotten it down to something small. So the wrangling is on the big data. So I would say we do, I think, a pretty good job of supporting big data wrangling. But when you get down to okay, now I want to run a machine learning algorithm on it, and I like PyTorch or I like scikit, at that point, we need to hand actual pandas data structure to the library. And that's, I think, interesting question as to how that could be improved in the future.
Thank you. You mentioned the Airbnb application. I'm wondering if you could introduce a couple of big data examples that were actually operated using AsterixDB.
Yeah, so what we did with those, so this is there's some publicly available data sets. And so we've done 2 case studies as in the process of building A-Frame. The first case study was a publicly available San Francisco crimes data set. And we had an undergraduate who had used Spark in a previous life as an undergrad to do some analysis. And we said, well, why don't you go do the same thing you did back when you did that project, do it using our stuff, and let's see how it worked. And so he went through the whole kind of machine learning process sort of to develop a predictor of where crime is going to occur in the same way that he had done using Spark. And we learned a number of interesting things, and we added some missing data handling and some other features that he needed when he was creating the features and doing the feature engineering. And then the more recent case study was one where, again, it wasn't like we were operating on their data. We actually downloaded a publicly available data set. So there was a blog that had taken Airbnb data and done some analysis of, where should you build things or where should you rent things and how should you set your prices. And so it was basically doing data analytics on data from Seattle. So we got that data set and sort of recreated that. And then we went and got publicly available data that Airbnb shares that had 40 cities. And then we did a scalability experiment where we said, okay, if we have more and more data and we want to do that same analysis, when does pandas run out of steam, actually run out of memory? And, how far can we go in terms of the number of cities? That was our kind of scale factor for that data. And let's look at the performance. And so that was an opportunity for us to say, let's do what somebody else has done. We'll walk through their script. We will translate that into A-Frame. We'll note all the differences, and they're fairly few. And then we'll, sort of try to learn, what else do we need to be able to do? And I think, to me, I think you pointed out probably the biggest open area is what happens when you're getting into the more, linear algebra side of pandas. What can we do there? And that's, I think, an area where we need to do some future work.
Thank you very much for your answers. Yes, this is the end of today's session. And tomorrow's session will begin at the same time, and we ask for your participation. Thank you very much for your participation today.